All right. Last thing that we're going to talk about in this section here is this idea of similar solids, and we did this a little bit last chapter. Now we want to focus on areas. So similar solids are solids with the same shape and all corresponding dimensions proportional. So identifying similar solids. Are the cylinders similar? If so, what is the scale factor of the first to the second? So to figure out if they're similar, we're going to do, and it says that the first to the second. So this one's going to be the first one, this one's going to be the second one. So I'm going to do 6 over 5, and I want to know, is that equal to 12 over 10? So if we reduce 12 over 10, this does equal 6 over 5. So yes, they're similar. And the scale factor is just 6 to 5. If this didn't reduce to the same thing as that, if those were not equal, then they would not be similar. Okay, so let's say it says here that consider cubes with side lengths of 1 and side lengths of 2. So basically we have two cubes that are in the ratio 1 to 2. So the surface area of the one side one. So if you think about this one, so again, I've got this cube. So it's a cube, all the sides are squares. So basically I have 6 squares that all have an area of 1. So the surface area is just 6 times 1. If I had the same cube, but now they're all 2s, then the area of one of those squares is 4. There's 6 of them, so 6 times 4 gives me 24. So if I think about the sides were in the ratio 1 to 2. The surface areas, so I'm going to have 6 to 24. But that's going to reduce to 1 to 4. And then the volumes, so the volume of that 1 by 1 by 1 cube, so the area of the base is 1, the height is 1, so that's 1. Again, it would be cubed units. The volume of the 2 one, it's 2 by 2, so the area of the base is 4, and the height is 2, and I get 8. So the volumes are in the ratio 1 to 8. So I got 1 to 2, 1 to 4, 1 to 8. How is 2 and 4 and then 8 all related? So, I mean, one thing you could say, well, 2 times 2 gives me 4, right? And 4 times 2 gives me 8. But the other thing is, if this is just 2, if I square 2, I get 4. If I cube 2, I get 8. Does that also work for the ones? It does, right? So if the scale factor of two similar solids is A to B, then the ratio of their corresponding areas, and remember, surface area is still referencing area, is A squared to B squared, and the ratio of their volumes is A cubed to B cubed. So this one here, it says two similar solids have volumes of 729 and 1331. What is the scale factor of the smaller to the larger? So this is the ratio right now of the volumes. So in order to get to the scale factor, that's the same thing as the sides, I have to take the cube root. Sometimes you might have to reduce first. We saw this a little bit last chapter. So if I do, let's see what happens here. So I'm going to go to math. I'm going to go to 4 and I'm going to type in 729. Oh, perfect. And I get 9. And then I'm going to go to math again and I get 1331 and I get 11. Perfect. And I can't reduce those anymore. All right, so for me to go from volume to scale factor, again, I had to take the cube root. Maybe it won't work out and you'll have to reduce it first, or maybe you'll take the cube root and then have to reduce it later. If I were going to go in the other direction though, then that's when I would take the number and I would cube it, okay? So here in the next one, it says two similar prisms have a surface area of 144 and 324. And it says find their scale factor. So the surface areas are in the ratio 144 to 324. How do I know which number goes first? Well, sometimes the problem tells me, sometimes it doesn't, and I just go in the order that the numbers are given to me. So now I'm going from surface area to the scale factor. So remember here, surface area is the square part, the scale factor is not squared. So to go this way, and now I've got to take the square root, and you might have to reduce. Again, the order of that can be different. Sometimes I take the square root first, then I reduce. Sometimes I reduce first, then take the square root. So I'm going to, and I know I can take the square root of 144, so I know that that's going to be 12. And then if I take the square root, oops, that's going to confuse you. If I take the square root of 324, fortunately I get 18. But I know that both of those numbers are divisible by 2. Actually, I even know that both of those numbers are divisible by 6. So I'm going to reduce this now. So 2 divided by 6 gives me 2. 18 divided by 6 gives me 3. So that's going to be my answer there. So again, when I was going this way, I just took the square root. If I was going from the scale factor to the surface area, I'd have to take the number and square it. So it depends on what direction I want to go, okay? Okay. So this problem right here says the volume of two similar solids are 128 and 250. The surface area of the larger solid is 250 meters squared. What's the surface area of the smaller? So you might want to think you want to set up a problem like this. So you would just have like 128 over 250 equals x over 250 and just solve it. The problem is that this right here is your volumes and this is your surface area. These are in squared units. These are in cubed units. So they're not comparable. So what I'm going to do is I'm going to take the volumes that I have already. When I start with those volumes, I want to back it out and I want to try to figure out what that scale factor is. So to figure out, I have the ratio of the volumes. So to figure out the scale factor, I'm going to take the cube root. So if I take the cube root of 128, I don't get a nice number. So what I want to do here is instead I want to try to reduce these. So if I do that 128 divided by 250, if I go to math, frac, I'll get 64 over 125. So the first thing I did for this one is I reduced. Sorry, I should label this the surface area. I should label this the volume ratios. So the first thing I did is, so I took the volume ratios, and the first thing I did is I reduced them. My goal is to try to figure out what the scale factor is, because if I figure out the scale factor, then I know what the areas are supposed to be in the ratio of. So what I want to do here is now I'm going to take the cube root. So now I'm going to take the cube root of 64, which gives me 4. And then I'm going to take the cube root of that 125, which gives me 5. So to go from here to here, I took that cube root. Again, so basically what I had here to start with was I had a cubed to b cubed. Remember, my goal was to find the other surface area, but I need things squared. Now I've backed it out back down to a to b. In the end, my goal is to set up a proportion. So I do want to find that x, so x over 250. What I need right here is I need to know the ratio of the areas. If the scale factor is 4 to 5, if I square the 4, so now I'm going to take these numbers and square it. If I square the 4, I'll get 16. If I square the 5, I get 25. So this is the surface area ratio. So again, here I had the volume ratio, which is the cubed one. I backed it down to the scale factor. And now I'm taking it back out here. So it's that a squared to b squared. I know I wrote that funny, but okay. Now I can cross multiply. So I would have 16 times 250, and then x times 25. I divide both sides by 25. So now x is equal to 160. This was surface area, so it is meters squared. All right, the next one says using scale factor to find capacity. So a bottle that is 10 inches high. So we have this little bottle, 10 inches high, and it holds 34 ounces of milk. So 34 ounces of milk, that's volume. And then we have this bottle shop over here, the sandwich shop, and it's shown at the right. It's shaped like a milk bottle, but it's 480 inches high. If we could actually fill it up, how much milk would it hold? So what I know here is that the ratio, the scale factor is 10 to 480. And then I could reduce that to 1 over 48. Do I have to reduce it? No, but why work with large numbers? The volume, so I know that remember right now I have this small bottle over the large store. The bottle can hold 34 ounces of milk. I don't know what the store can hold. I don't want to use 1 over 48 here because that's the scale factor. The volumes are in the ratio 1 cubed to 48 cubed. 1 cubed is obviously just 1. 48 cubed is this big number here. So then I would cross multiply here. Basically, I end up with that big number times L. So this large milk bottle, this large sandwich shop, would hold this many ounces if I could really fill it up. All right. All right, I've got a couple problems here to look at with you. These are the ones that kids kind of struggle with. So this number 16 here is one where, again, we're given the surface area, and we want to find the other volume, which is different, a little bit different from what we did here in the notes. So the surface area, and they give me the volume of the larger ones. So the surface areas are 192 to 1728. The volume of the larger one is at 4860. All right, so surface area. So the first thing I want to do, again, this is in that a squared, b squared. I want to back this down so I'm I find the scale factor. So I'm just a to b. So I would take the square root, but I'm pretty certain here when I take the square root of 192, it's not going to be a nice number. So first thing I'm going to try to do is I'm going to try to reduce this. So I get 1 over 9. Isn't that crazy? So this reduces to 1 over 9. So then when I want to find the scale factor, remember these are squared, so to back it out, I'm just taking the square root. So the square root of 1 is 1. The square root of 9 is 3. And then it tells me that the volume, they gave me the volume of the larger figure. So the volume of the larger figure is at 4860. I don't know the volume of the smaller figure. I can't use 1 over 9, that's the ratio of the areas. I can't use 1 over 3, that's the ratio of the sides. But I could take 1 over 3 and I could cube it. So I could, 1 cubed would just be 1. 3 cubed is 27. Now, then I can cross multiply now. And eventually I'll end up with 4860 divided by 27, because 4860 times 1 is still going to be 4860. So then I get x is equal to 180, and the units on that were meters, so this is meters cubed. 20 is like the one in the notes, so I won't do 20 with you, but then we'll look here at 21. So 21 says that there are 750 toothpicks in a regular size box. If a jumbo box is made by doubling all the dimensions of the regular size box, how many toothpicks will the jumbo box hold? So it's a regular size box. Basically, so the scale factor is 1 to 2, right? Because you have the regular box and then you're going to double all the sides. So the volumes are going to be in the ratio 1 to 8. Because to get to that, what I did is I took those numbers and I cubed them. So if the smaller one, so if I have 1 to 8, the smaller one has 750. I don't know what the larger one has. I cross multiply here, I get x. So then 750 times 8 gives me 6,000. So it would be 6,000 toothpicks. It's a lot of toothpicks. All right.